Hi, everybody, and welcome to the last session of the day. Thanks for hanging around this long if you're still with us. It's been a long day of really interesting talks and presentations and good chat, actually. Great questions. So, not long to go, and let's dive straight in. So, I think we've had a lot of chat about different routes forward, hydrogen batteries, and other technologies. I've said I'll do a piece on hydrogen and looking at actually how practically we can bring hydrogen into rail. The first part of what I'm going to talk about, I think we've covered in quite a few of the other presentations, so I'll probably whiz through quite quickly and then spend maybe a bit more time on the second part and questions at the end. So just briefly, let's start off with thinking about decarbonisation of rolling stock, what the situation, the challenges are. So I think we've all discussed, and I've got the word UK in there, but we can replicate that to Europe and wider around the world, that really transition to low carbon traction, requires both new rolling stock and upgrades to existing fleet, because we have a very large pool of existing diesel vehicles out there. We can't just not do anything with them. So that's clearly an area of focus. Converting that to a sustainable source of propulsion is very attractive, whether that's with direct replacement fuels or otherwise. There are some complications. So remaining life of these vehicles is limited. The business case for complete replacement of the engines can be poor. There's uncertainty around government plans, certainly in the UK. We heard Clive Roberts earlier talking about needing that consistency of vision moving forward. I suspect it's similar in many other countries as well. We need an optimized approach. Again, we've sort of looked at some of the logistics and supply side in some of the earlier talks. We really need it to be a unified approach and holistic around what we're trying to achieve, and making sure that all the rest of the infrastructure is in place for that. And the technology is moving along at a rapid pace across all transport sectors. And we need to understand that we are operating in a sector that typically has very long asset life. So technology moving at a high pace is a challenge for us. So optimized investment decisions against that are very difficult. So today we will look at, okay, so how do we possibly move the pathways forward for that, and see some of our insights from rail and across other sectors. Very briefly, Ricardo, our background really is in propulsion systems design and development for 100 odd years, but we also have a strong capability in rail. We have about 700 people around the world that work in the rail industry specifically. We also do environmental analysis and energy systems as well. So it's quite a wide breadth of capability we now have. Brief background, won't dwell too long. I think we've covered this a lot, but there's a lot of work that's gone on into decarbonising transport, decarbonising rail within the UK. We've got Network Rail, RSSB, DFT, Rail Delivery Group, and so on, all looking at these issues, as well as those operators within the rail industry, those supporting parties like ourselves outside and around the rail industry, and so on. And this is similar in most countries. What's the strategy for the railway? Well, in the UK, we've done a piece of work called TDNS. I say we, Network Rail, have, but everybody's fed into it. And within that, there's been an identification that even if we electrify large parts of the rail network, we're still going to need solutions like hydrogen and batteries to take us forward. So why is it so difficult to implement these things in rail? We've seen it in automotive and commercial vehicles and so on, and they seem to be ahead of us in a lot of the cases. So rail is a very heavy industrial environment. The duty cycles and the requirements of use in rail are very demanding. Often have a very complex stakeholder investment makeup. It's quite like the marine industry in many cases, where you have owners who are not the operators, operators who are not the owners, government intervention, and so on. And it's very difficult to invest securely in that type of environment. clear policy and consistency of regulations, they're changing. We're also, let's be honest, something of a political plaything at times. And that links into the industry drivers. They're often changing on a regular, reasonably often basis, depending upon the political flavour of the month. Taxation, charging, incentive schemes. Can you operate inside urban environments? This type of thing. These are all being placed into rail as well, but there's uncertainty about them and when they're going to come in. And finally, we have things like standards creep. So we have developed to a set of standards to ensure the safe and compatible and reliable work of a rail network. And that creep of standards is something that's built up over 200 years while we've tried to develop this safety within the rail system. So you can imagine that there's a lot of demands and a lot of standards that need to be put in place before we can actually put something into service, which makes it expensive, difficult, and time consuming. So why is the solution space so complex? And again, I think we've gone through most of this today, but effectively we have a variety of sources of energy we're going to create in the future, or generate, I should say. From that, we need to use that in one way or another. So directly using the electricity is obviously the prime route forward, but if we can't directly use it, the next best thing in terms of efficiency is probably store it as in batteries as chemical energy that we can then use directly. But if we have to, we can stick this into as hydrogen, and then we can use that hydrogen in combination, typically with batteries, to run. But we can also use the hydrogen as a fuel for an internal combustion engine. Or we can use that hydrogen to create other synthetic fuels and run those in a combustion engine, or we can biofuel those combustion engines. So what are the issues? And these are just sort of rule of thumbs, but you can see some of the issues in terms of mass and volume that we have to accommodate within our already very constrained package environments in a rail vehicle. And that's really the nub of the issue. And I think, again, we've gone through that a number of times today. We want to maximize the space for our passengers. We are quite constrained with the available space on vehicles for putting this stuff, particularly in the UK, where we have a smaller vehicle gauge than a lot of Europe. It's difficult to stick stuff on the roof, for example. So these are all issues that we have to overcome. And something we've talked about a number of times, the most efficient way to use the energy. There's going to be a limited amount of this energy as we transition away from fossil fuels. We are going to have to produce more energy to support the transportation network. Added to the growing industrial energy demand and growing domestic energy demand, that all puts a lot of constraint on our system. And so really we want to use it as efficiently as possible. So all of that has to be backed up and supported in our decision process by understanding the technologies, understanding the rates of maturity of these technologies, what we can expect from them, what their level of development is to help us with those decisions. Do we do something now? Do we put off doing something for 5 years, 10 years, or so on, until the technology is at a suitable level of maturity? So what does that mean in terms of hydrogen in rail? I'm very much of the opinion, there isn't a particular solution like everybody else has said today. Hydrogen is going to be in the mix as something that is going to help us on this journey. It's not the be all and the end all by any stretch. So it's going to be a niche application in the most part for rail, but it's still going to be something that's needed. But it might work in terms of looking at future connected cities. It may work where there are other demands for hydrogen, so heavy duty transport on roads and logistics, perhaps private taxis or hydrogen buses where batteries won't do the job as well. So looking at integrated transport systems. We also need to understand what our energy systems are on board. So we've talked about electricity and batteries and hydrogen, but we've also got biofuels and biogases, potentially even mechanical or cryogenic energy storage systems. And we also need to know about integrated, local renewable energy systems. So, are we going to generate energy on site with local solar, PV, or wind power, or other, hydropower schemes, and so on? How do we integrate those into our network? All of those, hydrogen can play a part in terms of an energy storage system as an energy vector that we can use to help transmit that energy and store that energy that we're producing. So I think we've gone through the why hydrogen, but where in rail particularly it fits is, as we've said today, long distance, high energy consumption application. So, rail is one, heavy duty trucks, bus, coach, where they've got to do long journeys, aviation, and marine. Centralized hubs are going to be most likely where we produce at large volumes, and then we share that centrally across a number of different transport modes, perhaps at typically distribution centers where you might have a rail terminal, a heavy duty goods terminal, and so on. So that link is likely, airports, out of town destinations where we can fuel central fleets, and it's likely to have other hydrogen users. Will hydrogen on its own in rail make a solid business case? Possibly not in many cases, and that's where we need to be thinking a bit more holistically about the whole transport system. What are the options when we have hydrogen, I guess, and this is where we're getting into how do we socialize it. So hydrogen fuel cells, I think, definitely the future. Generate electricity directly. They will fit within our electrified propulsion system platforms. They're quiet, they're zero emissions at point of use, so great for cities and urban environments, and they've got good quoted efficiency. Alternatively, we also have hydrogen combustion engines burning the hydrogen in a combustion engine. What are the advantages of that? It's a stable and known technology. It's very tolerant of poor hydrogen, which we have quite a bit of at the moment. It's robust to poor air quality. Again, the fuel cell can be quite sensitive to operating in dirty environments, and it's durable and reliable. We know the technology. We have supply chain geared up to working with internal combustion engines, whereas all of that's still not quite there with fuel cells yet. So ultimately, the fuel cell technology hasn't really been proven to be mature yet for a rail application, and it also doesn't have a mature supply chain to support it. Whereas with the hydrogen internal combustion engine, we see quite a mature supply chain in place. We see the technology potentially being readied quite quickly to a point that, we know a couple of years and we can develop a pretty robust product, whereas fuel cells, the development cycle has been going on for 30, 40 years, and we're still not at that fully robust product yet. Very briefly, how do they work? I won't stop too long on this slide, but a fuel cell stack is a chemical energy production using proton and electron, a proton exchange membrane. Typically, there are some other solid oxide fuel cells and so on, but PEM is the technology really for rail vehicles that we're seeing. We need some additional pieces of the system to process and manage the air and the hydrogen that you need, and to cool it and so on. Some thermal conditioning, but that's generally it. Very few moving parts apart from pumps and so on, and it's quite a simple system. Internal combustion engines, these are much more complex systems, but we know them very well, and we spent a long time developing them, so they're pretty robust now after 100 years of development. They are conventional four-stroke cycle. It's running in hydrogen mode, a spark ignited 100% hydrogen combustion system. So that's very similar to a gasoline engine. And in hydrogen, we're likely to need some after treatment to clean up the gases. There will be some NOx from the high temperature of the combustion. Shouldn't be much in the way of particulates, because it's a gaseous fuel with no impurities in it, although we will burn some lubrication oil in there, so that will give us a small amount of particulates to deal with. What's the difference? Well, um, hydrogen fuel cells theoretically are more efficient than a combustion engine. And when we're running them in the most efficient mode points, which is typically between about 25 to 50% of total system power, then we get a really good efficient system. The fuel cell on its own will run at about 60% efficiency at the moment. When you add in all the other bits and bobs that need to go with it and the conversion into motive power, we're looking at about 50% as a peak efficiency, which is pretty good. An IC engine, on the other hand, will be lower efficiency at those part load conditions, but where they're running at high load conditions, 70-80%, that's its peak power efficiency or peak efficiency range, they're going to be pretty comparable to a fuel cell system. What we can't do with an internal combustion engine that we would be able to do with a hydrogen propulsion system is recover regenerative braking energy, because with the hydrogen fuel cell, you'll typically have a battery alongside it where you can recover the energy, and we don't typically have those with internal combustion engines. So I won't dwell too long, but these are our examples between them. So you can see that actually within the operating cycle where we are without a battery, we're typically similar on overall efficiency. We're worse on an IC engine compared to a fuel cell in terms of emissions at point of use. We're well understood in terms of the technology though, but we're more noisy having an engine with combustion going on in there. However, we're more tolerant to contaminated fuel. We're probably more robust. We're probably more durable at the moment, and we have much better grade heat, if you like. So we've got a high heat source coming out, so we can recover energy from that high grade heat source as well and use it for heating and ventilation systems and so on. One of the key points, though, is, and at the bottom is price. And at the moment, the price of a comparable fuel cell system is significantly higher than a comparable internal combustion engine. And that's really one of the points at this time for the commercial type of decisions moving forward. What we also have when we've been talking about the environment and so on is we don't have a requirement for those, if you like, environmentally sensitive batteries in terms of the minerals and materials you need to create them. The materials for creating an engine are very simple, very sustainable, and very recyclable as we are at the moment. What we can see is a significant uptake in ICE engines for hydrogen by all of the major manufacturers. Again, these are the ones that have publicly said that they're developing engines. I can rest assured that the rest of them are have probably not announced that they're developing engines, but it's likely that they are. And this is because although these businesses are all investing in hydrogen fuel cells as well, I think they are seeing the commercial demand from their customers driving them towards the hydrogen internal combustion engine solution to tide them over until such a point as you can make the commercial case for fuel cells. So is it the right time for hydrogen internal combustion engines? I think at the moment, the technology is relatively proven and robust. What's interesting is you can convert your existing hardware. So we have a whole fleet, thousands, hundreds of thousands globally of diesel engined rail vehicles, many of which are relatively new with emissionized diesel engines, particularly when they're large, expensive engines in locomotives and so on. That's a very big commercial risk to throw that engine away and try and replace it with a completely new propulsion system. If you can convert that, that's significant saving. And what that allows you to do is invest that cash that you would be putting out in terms of your retractioning your vehicle, and you can invest that cash into the infrastructure and operational logistics side, the socialization of the hydrogen, and stagger the investment that's required to transition over to hydrogen. So we can look at hydrogen internal combustion engines potentially as a stepping stone technology that allow us to sort of minimize the pain, if you like, of our transition into a hydrogen future. And that's really the key thing. We're not saying it's either or. We're saying that these things are going to work in parallel. For new trains, if we're building a new passenger train, for example, yes, a fuel cell is a perfect application to do that as in limited numbers, if we can make the commercial case make sense. But for the existing fleet and for those locomotives that we've got running around everywhere, then potentially hydrogen internal combustion engines are actually going to be a much better solution in the short term, until we're looking at 10, 15, 20 years down the timeline when we're looking to replace those assets. So I guess, what are the challenges and the opportunities? So safety, safe use of hydrogen in rail. This is probably the biggest challenge I think we have. Technically we can make it work. It's all about sensible and robust engineering, but safe use is the risk that everybody fears. The rail system has to be, I say, entirely safe as it can be. We aren't scrutinized in the same way that road transport is, for example. People die on the roads every day. People do not die on the rails every day. So, and that's a very different paradigm that we have to operate in. Onboard storage and volume, cost and supply of hydrogen are clearly still issues. But where are the opportunities? So what does hydrogen help us with? It reduces potential costs of grid connectivity. It can be 50 million plus to connect a high power grid connection to provide traction energy for rail, and that's just not feasible in low utilized lines. It can support multimodal business case for hydrogen hubs. It facilitates actually building new renewables energy production schemes where you can't necessarily connect it to the grid, but you've got plentiful renewable resources. And rail can provide a really consistent consumer for the supply chain. So again, provide the supply chain guaranteed investment or guaranteed end customers to support their investment decisions. So there are definitely pluses there, I think, for us. So just to finish, what's a view of the future potentially look like? This is UK centric, granted, but you can transpose this to other areas. This is looking at freight as an example, but we've got our core freight networks going up and down the country, but it could equally be passenger trains. And what does that potentially look like? So we've got freight coming in from the continent. How does it get up to how does it get up the country? So we've got potential for using overhead wires where they exist, and absolutely that is the right way forward. That's our yellow line there, but our green line represents a route from a port to container terminal. Felixstowe, which is our largest containment terminal in the UK, doesn't have wires. So that green line there is your ideal hydrogen line for a train rather than a diesel hauled train. By having that hydrogen line, that presents us with possibilities. But sticking with the electrified line for a moment, you can imagine that up at our yellow dots at the top there, we've got a distribution center. So the rail freight comes in and it gets distributed. And that's our nice distribution center by the motorway there. And we can have a fleet of captive electric trucks, because right now it's very difficult to make a long haul 44-ton HGV work with batteries, but we can make short local captive fleets of HGVs work, and they can distribute the goods with a battery electric system in town, cities, and in the local urban environments. Equally, we can have a hydrogen hub here. At this point where the hydrogen train comes in, it's going to need fueling up. We may as well put it at a distribution center, and again, then we can fuel a fleet of hydrogen HGVs that can take the traffic that can't go on the rail freight, but need long distance journeys as well. And so you can see that thinking about the whole transport system, that starts to give us opportunities where perhaps there had been opportunities previously. And you can see that potentially there are other sort of crossover points on that journey at other distribution centers where you could build these hydrogen hubs and start distributing that hydrogen into the wider transport network as well. So that's a potential view of the future. Not saying that's how it looks, but what we have to start doing is thinking about rail as just a part of a wider system when it comes to these future technologies, and not keeping a very rail only bubbled or rail centric view of things, and that's really going to unlock the door to these new decarbonized technologies.